thank you. Now complex analysis becomes extremely interesting. It's already interesting to me. We discussed last time basic problems. Problems. And let me just, so on X, which should be a Riemann surface, but it could be just a domain in the plane, so. Maybe I'll write the problem 1, 2, and 3 here. Under what conditions is given meromorphic function so you give me a meromorphic function M, the quotient of two homomorphic functions where f and g are homomorphic. That's an interesting question. It's true locally, but it's not, by definition it's true locally, but the question is the global question. So, global. Similar question, but for divisors. I'll formulate it in a shorter way. Given B a divisor on X, is there a meromorphic function meromorphic on X with the divisor of the meromorphic function, the given divisor. And finally, third case, given distribution of principal parts, you see, we complain about German being so long. The words are so long, but to say distribution of principal parts is also a long expression. So just remember, this is Hauptteilverteilung. Given the distribution of principal parts, call it H. Is there, that's prescribing at various points, just like a divisor prescribes at various points. Is there a meromorphic function with this principal part distribution? These were formulated in terms of some mappings from meromorphic functions. Here, there's a meromorphic function from meromorphic functions to divisors. And you're talking about the image of this map, and here's the meromorphic, these are homomorphisms. And here you should remove the non-invertible ones, otherwise it could be locally zero. And here, meromorphic functions to principal part distributions. These are group morphisms, and so they have some decent properties. And but it's highly non-trivial to just determine what is the image of these things. So those are the three guiding problems in complex analysis at the beginning. And they are global problems. But nevertheless, we want to study these problems involve certainly poles of meromorphic functions. You have to understand the polar sets and zero sets of meromorphic functions, but say I'll formulate in terms of poles of meromorphic functions. For example, at z equals 0, we have a meromorphic function of z, which has a certain principal part plus holomorphic terms. This is the way we think about principal part distributions at 0, and this is the way the polar set works. So then an obvious question. Yes. An obvious question is, given, so if you're looking at this, we're looking here a little bit locally, but so given f holomorphic, say, on the punctured disk. So that notation is an abusive notation, but I'll use it nevertheless. Maybe a disk of radius 1 to make it precise. The set of z such that z is not 0 in less than 1. Given such a thing, how do we figure out if it is meromorphic, for example? Well, let me write it. If it's meromorphic, f extends to a meromorphic function on the disk. I think that's a reasonable question. You're standing outside of 0, you have some function there, and we want to know whether or not it extends to be a meromorphic function or not. Okay, so one thing you need to learn how to do is to say that you have a map, and this is a really good map. It's called restriction. You have the meromorphic functions on the disk to the holomorphic functions on the punctured disk. No, let me write this. This is correct. So that's of course nonsense, because it can have poles all over the disk, and if you restrict, you get poles. So let's say meromorphic functions with poles at 0. So we have a map, That's a very good map, right? And you should try to formulate big questions with a lot of words in it. You see, if I write this in a seminar in downtown, I don't know your local language, but Kyrgyzstan language, whatever it is, it's some complicated language. In Moscow, I don't know, in mathematics you speak more or less English when you grow up in Kyrgyzstan or not? Maybe not. Russian. Russian. I don't know Russian either, I was hoping. Yeah, but I mean, this is a complicated statement. And here we have a map, and I'm asking you to determine the image. That you can write explicitly in mathematics in a clean way. What's the image of this map? That's the question. So the question is, which meromorphic functions, which holomorphic functions can be extended to meromorphic functions on the disk? So determine image. So when you're studying something, you should really try to formulate it in terms of maps. I think that's something I've learned over time. You should do that, and then make your statement precise. Determine the image. Okay. So you see, anybody in this room can ask these questions, and Riemann asked these questions, and we note that if n is a meromorphic function with only poles at 0 on the disk, then the growth of n near 0 is understandable. Right? Because we just looked at what it is. If it's extendable, it looks like this. Right? And so you see this growth is not too bad. And so, so a reformulation of the question of the above question, reformulation are, oh, there's a wonderful, again, you see, German's really good. Präzision is the beautiful word in German, to make precise. Can you say that in one word in English? Making precise. Yeah? You see, it's the advantage in German to make a verb a noun. You can make a verb into a noun much better than you can in English. To make something precise. Right? That's a noun into a verb. I don't know. Reformulation. Make a precise version of the above. Yeah, let's just say Z to some big power of n. You see, I learned physics when I was some time ago, and if you write a big N, your physics people will agree that when physicists write big N, it's big. But it's usually, by the way, it's usually 1 over n is small. And yeah, it's true. And then quite often we think of this as Planck's constant, some small number, 1 over n. So for example, you should think if you have a huge number of particles in some system which are interacting and doing all sorts of stuff, there's no quantum mechanics. It's classical mechanics. Yeah, that's the way you should think. And that's the reason 1 over n should be Planck's constant. And now you see, if you take n to infinity, this is everybody lies. Planck's constant is a constant. It's a number. By the way, if you don't believe me, go to Göttingen and go to Max Planck's grave. Oh, by the way, it's a perfect grave because physicists always have money, and they made a perfect grave. And on Max Planck's grave there's some calculation of h bar, right? It's very nice. If you go to Göttingen and check it. You go to Hilbert's grave in Göttingen, you need to cut the grass. And it's terrible. No, it's probably, but when I was there, the grass needed to be cut. I felt so bad about it. And the gravestone, the Grabstein up there, so the gravestone was a little bit, Planck is perfect, Planck constant, everything. Yeah. But what one says here, you see, there's no, this constant is a positive number. That means there's quantum mechanics. But if this constant would be 0, there would be no quantum mechanics. So what the idiom here is you let n go to infinity, and somehow, in some way of speaking, Planck's constant change to go to 0. That means there's no quantum mechanics. That's of course nonsense, because a constant is a constant is a constant is a constant. But you have to think, you look at 1 over n limits, which in some sense are forcing quantum mechanics to 0 when you have a huge number of particles. Or you have a very high temperature, or something like this. So, anyway, so you make precise version of the above. That means you take z to some huge constant, and you multiply it by this function f we don't know, and this thing should go. This thing should be at least bounded. Well, if it's bounded, then I make it to another constant and I kill it. So this goes to 0 as n goes to 0. For some big n, for some some n, perhaps very big. This goes to 0. Yeah? That's a reasonable way of saying this function is not too bad at 0. It has maybe a singularity at 0, but you can kill it. Right? Who knows? Maybe it's just some completely insane function, but you can still kill the singularity. Yeah? So we come to, this is a question, this was asked by Riemann. You see, everybody in this room can ask this question, even I. Yes? And you need to work on asking questions. If you're interviewed by Google, they do not care that you know some mathematics. They care if you can ask good questions. I guarantee you. So Riemann asks a question. What is the question? If this is the case, then M is in the, let's call this the restriction map. Then M is in the image of the restriction map. That would be a question, right? If you can kill the singularity by multiplying by z to the n, and that says it doesn't have a bad singularity. Okay. Well, in other words, let's write down a lemma. And this lemma has a famous name. It's called the Ewigkeitssatz. It was formulated in this way by Riemann. The word Satz means theorem, and Heben means to live. Yes? And if you put a bar on something, it's not like drinking it. It means liftable. That's precise. You could put a bar on anything like that and make it a bowl. Okay? So liftability, you put a kite on it, makes it into a noun. So this means liftability theorem. Theorem of liftability. It says you can, and Riemann was thinking in terms of lifting the singularity away. And the theorem is you see what, if you formulated this, nobody formulates it this way usually about growth. I'm very insistent on discussing growth. And you see Riemann was thinking in terms of growth. You see, if you multiply by z to the n, you kill the singularity. It's liftable. That's the way to remember it. You lifted it away and threw it away. There goes the singularity. Almost. I used to play games. So liftable singularity. If F holomorphic there has weak growth. I purposely formulate like this because we have to determine what is weak at the end of the theorem. So we will, right, it is some weak growth. Here I said it go to 0, but maybe it can be, it can grow a little bit. Well, let's see. Weak growth, then F extends homomorphic. Okay, let's prove that theorem. And in the course of the proof, we will see what weak is. Okay. Everything you learn in mathematics education is terrible because it tells you what to do and then you do it. Isn't it true? Isn't it true in high school? Isn't it true in Mathematische Olympiade? Isn't it true? They tell you to solve this problem and you either solve it or you don't. Right? It is stupid. So the question here is, what is weak? Right? What is weak? Well, let's see. Let's draw a picture of this thing. Here's 0, and F is holomorphic in there. This is the disk. And F is holomorphic in there. And it has a bad singularity, perhaps at 0. God only knows what the singularity is. Okay, so we say, I don't care. What I'm going to do is I'm going to cut a hole around this guy. And let's see, the orientation is this way because you're going this way, and the orientation here is this way because I'm regarding this as an annulus. This is the annulus here, annulus of outer radius 1 and inner radius epsilon, if this thing is epsilon. Okay, that's called an annulus, right? And now we know the Cauchy integral formula for anything. The Cauchy integral formula is a formula for anything. So let's say integral f of a point in this thing, zeta, f of zeta equals 1 over 2 pi I. I'm going to write this out long, boundary of the annulus, f of z over z minus zeta. d z. Z in the boundary of the annulus. Okay? Isn't that true? You put a pole here at this of order 1, and you pick up the value of f of zeta. Okay? Let's emphasize, let's call this thing A epsilon. Again, everybody in this room can do that. And then everybody in the room should make a mistake. So you have an idea that may be bad, maybe not good. You have this idea that f of zeta You have the Cauchy integral theorem. F of zeta is the integral around the boundary of the disk, f of z over z minus zeta. You have this idea. Because the function is going to be holomorphic on the disk in the end. Right? So that should be the case. Yes? So that should be the case. Again, in the end, if we can prove this theorem, this should be the case. Okay? So you have this idea that the function should be represented by the Cauchy integral operator. You should write that in your brain. The function should be represented by the Cauchy integral operator. This is a very interesting operator. You go to f, you start with f, and maybe we call this I of f. Any f, if it's defined here on the boundary, I can assume it's defined because this thing's locally, so I can assume it's defined on the boundary. They're continuous, wonderful. The f goes to, is mapped to the operator, the Cauchy integral operator of f. Right? That's very interesting mapping. How many times do I have to scream at everybody in life, write everything down as a mapping? This is the Cauchy integral operator mapping. It maps continuous functions, for example, to holomorphic functions. If you're lucky, you start with f here that was given to you outside, and you get the f, you get your old f. It's sort of a fixed point of this Cauchy operator. Yeah? And this thing is a holomorphic function on the whole disk. That's fantastic. That's a fantastic operator. It looks like this. It's called orthogonal projection if you're lucky. Here's the holomorphic functions on the disk, and here the whole thing is the continuous functions on the boundary of the disk. and here's a projection onto the holomorphic function. Isn't that unbelievable? You can project functions and get holomorphic functions from continuous functions. Incredible thing. And what you've done, you're hoping that that's what you've done. So you have this idea that that's what you've done, but you may be in trouble because you may have a big problem with the singularity. You see, what we've written down here is not the Cauchy integral operator. We've written down the Cauchy operator on the annulus. Right? On the annulus. I don't know where it is now. On the annulus. Okay? So this thing on the annulus, integral on the annulus, on the boundary of the annulus, this thing here, this is a good guy. The trouble is, we may have problems of zero, so we go to zero. Let's look at what happens at zero, dz. Yeah. Well, where is zeta? Zeta is far away from zero, and z. No, I don't want to do that. I'm sorry. Well, okay, I do want to do that, but let's look at this inner integral. There are two integrals here, right? The two integrals. The outer integral. Let me write here. The 1 over 2 pi integral around the boundary of the disk of radius 1 plus integral, or minus integral around the boundary. Okay, I'm tired of 1 over 2 pi I. 1 over 2 pi I integral on the inside disk. Right? Because the orientation is the other one, minus. So this is the guy we're trying to figure out, right? So let's look at this integral. Okay. Well, dz, z is equal to epsilon r, the radius is epsilon, e to the I theta dz equals epsilon times I, that kills the 2 pi I, e to the I, d phi, right? And I'm supposed to put this in the integral, right? And now look, this thing, z, where is z? Z's running around on this boundary here. Z's running around on this boundary here. Z stays far away from zeta. So 1 over z minus zeta is bounded. If f is bounded, all we have to do is estimate this dz part, but this dz part is epsilon e to the I phi, and epsilon and the z to the I phi is just going around the boundary. That gives you integrated, that gives you 2 pi, right? So we're left with epsilon. So this is approximately epsilon times the behavior of, I'll be British for a minute, behavior. You know, British put a U in this someplace, behavior. Epsilon, the behavior of f as z goes to 0. Isn't that right? So it says that if f grows no worse than 1, right? So it says if f, now let's see what it means. If f, now I have to understand, what do I write here, big O or little o? Right? You guys were in my analysis 1 class, you ought to know that. I've forgotten. Let's see here. It grows slower than 1 over epsilon. Right? Grows slower than 1 over epsilon. What does that mean? Okay. If f grows slower than 1 over epsilon. So then this goes to 0, right? Are there any questions?
Do you say that z is the product of epsilon e to the alpha dz times epsilon?
Oh, I'm sorry. I parameterize the boundary with z equals epsilon e to the I phi.
Yeah.
And phi runs from 0 to 2 pi. So dz, so phi is running. So I get a d phi, of course, when I run,
Yeah.
but I get, of course, that's a parameterized thing. Sorry, thank you, I just confused you. Yeah, something bothers you.
Yeah, but we don't have I at the first one, and then you.
Yeah, okay, so, yeah. Okay.
Should it be dz equal to that?
Yeah, it is.
You're
Well, dz on the boundary, but
relatively fast.
yeah, if you like it. But yeah, dz. Yeah. That's really a theorem. That's called the Huckleberry. I read, what is the theorem? If the theorem is, the Huckleberry is, if f in absolute value grows more slowly than 1 over absolute z, as absolute z goes to 0, then f extends holomorphic. We just proved it. All right, what is the proof? Let's go through it again. Where is the proof? There it is. No, that's not it. Where is it? But here it is. Where's the end of this? Where's the integral over the boundary of the end of it?
Yeah.
Huh? Ah, yeah. F of zeta equals this Cauchy integral, not that Cauchy integral over the outside boundary. Right? Well, in the end, it is going to be the integral over the outside boundary, because we proved that the integral over the inside boundary is 0. Why is it 0? Because the integral, as you take the limit, the integral over this circle and the integral over this circle are the same. Right? By the Cauchy theorem. Right? By the Cauchy theorem. So as you take the limit, I'm allowed to take the limit, and as I take the limit, I use the fact that this has weak growth, then it extends. Here's the statement. So, and another thing you see in German that's very nice, I don't know how to say it in English, it's Zusatz. It means an additional remark here. F extends meromorphically. That was the original question. So F is in the image of this mapping. Is in the image of the restriction mapping, if and only if z to the n, for some big n, goes to 0, as z goes to 0, for some n. So, I hope you see that this was a sequence of questions that anybody can ask if you're sitting there thinking. And Riemann asks these questions. Riemann asks these questions. Right? He wants to know how to characterize functions here that have really a pole at 0. And the statement is, to have a pole, it should grow like a pole. Right? Because that's the statement, z to the big N times this thing kills it. Right? To have a pole, it should grow like a pole. That's an interesting statement. So then, of course, everybody looks for an example which is not extendable. I think extendable is spelled with an I. Can anybody help me on that? Is it spelled with an I or an A? I never know. Oh yeah, you got it. Phone. Let's see. I write it so many times. I always have to look it up.
Extend. E-X-D-E-N-D-A-D.
Yes. Okay. My wife, I ask my wife always, she tells me some rule, but I understand mathematics a little bit, but I don't understand rules in spelling. So not expend, thank you. Fortunately, we have the internet. Example of not extendable. F of z equals e to the 1 over z. Now, one reason you think that this is not extendable, this is a convergent power series, and we're going to talk about this in a minute. For a minute, this is 1 over n factorial times 1 over z to the n. N equals 0 to infinity. So you see, this does not have a good principal part. It has an infinite principal part, in some sense, right? It's an infinite principal part. 1 over z, I don't know, and so on. Oh, we have to put this, make it converge. 2 here. So that looks bad. That looks bad. Let's prove that it doesn't. It's not locally bounded. In the above sense. Let's prove that. Let's prove it. Let's look at z to the n, e to the 1 over z. This is z to the n. Oh, big N, because we're doing physics. Big N, e, and here you lock yourself in a closet for a little while and you realize that the absolute value of e to something complex is e to the real part of that thing. Now, you were really worried about this because you're a beginner, but then you have the courage to write down something like this, right? Right? Because e to the ix is in the circle, has absolute value of 1, and the exponential map is a homomorphism, so it's e to the x in absolute value, which is it's a positive real number, times the absolute value of e to the iy, and e to the iy is in the circle, so that's e to the x, and that's e to the real part, and that's that, right? And so, for example, with z real, say z equals x, so we have x to the n, e to the 1 over x. All right? X to the n, e to the 1 over x. All right? And that goes to infinity for all n. Right. Okay, so that's not locally bounded, so that we know Riemann's theorem that thing cannot be extended homomorphically. We have this feeling because it has an infinite extension. So here, that's a perfect example. Now, I've given a lecture with 3 blackboards, and every one of the statements on this lecture, I purposely made statements that everybody in this room can make. Okay? Every statement you can make. And so that's the kind of, if you're going to be a professional mathematician or a professional physicist or professional computer science, go into the private sector, whatever, that's what you do. And particularly with the ability nowadays of communication with information. This is a faculty for mobility of information, I saw that. Communication, yeah? No, there's a major point. You see, there's a huge amount of information, but you have to ask the right questions to lead you. I mean, here the information is trivial, right? I mean, anybody can do this. Any beginner can do this. But you have to ask the right question, and then maybe to get the information is hard. But so you lock yourself in the closet with a very fast computer and with several friends who work at Microsoft, Google, and Harvard, and you communicate with them. No, That's what I do every day if I don't know something. Yeah? Yeah, and I know who knows. That's the key. I know who knows, right? And I know how to ask the internet a question, right? You do too. Probably better than I. Yes. Okay. But that's all there is. Mathematics is that. And that's perfect. Riemann didn't have any of that, but he could ask a question. Right here, the answer, the information required to answer the question is true. Okay. Keep that in mind. I'm sorry I continue to beat that in your head. So, this motivates, having seen this, taking a look at an annulus. Let's look more closely. This is going to be a local global thing at annuli. So I use a notation, and I can always make the outer radius equal to 1 because I can stretch it or contract it. It doesn't change anything. So let's look more closely at this. You can also ask that question yourself. The inner radius is r, the outer radius is 1. This is an annulus, A, R, and 1R. Just occurred to me, several remarks occurred to me here. My son, we named, after my father actually, who has my first name, Alan, A-L-A-N. And his middle name is named after my wife's father, who's named Robert. And so we call him A.R. Alan Robert. So now I will call him an annulus. So he is an annulus. He'll be very happy about this because of the following fact that I will prove for you when I have a few more tools to deal with. It's a very beautiful and a key fact that Alan Robert is biolomorphic equivalent to Alan Robert hat. By the way, Alan Robert is a professor at, he's a pianist, maybe you've seen him in the web. He's a professor at the University of Iowa, and he gave me this jacket from the University of Iowa. So, Alan Robert is equal to biolomorphically equal to R hat. Can you believe this? This is a remarkable theorem, and something really is going on here. Yes. Habeck doesn't believe it's true. It's unbelievable, right? Yeah. The only parameter for that says there is a family of annuli. Yes. It varies as R varies. These are different. These are different. Of course, they're all diffeomorphic and so on, but they're different biolomorphic. So we will prove that. So let's look more closely at annulus. Let's write the Cauchy integral formula. We just did it. So f of zeta equals, well, let's look at this here. F plus minus F minus. Well, what do I mean by this? Let's first of all write F plus equal to what it is. This is the integral on the outer boundary. Let's write, just to remind ourselves that this outer boundary is the boundary of A. Let's call it A plus, and the inner boundary is the boundary of A minus. Just plus and minus to indicate it. So Cauchy integral thing, f of z, z minus zeta, dz. I'm writing Cauchy kernel all the time. For some unknown reason, I'm writing it out. It's a very important integral kernel that I like, so I write it out here. Right? Oh, and this is f minus. Okay? The two integrals. Difference of two integrals. Okay? Well, let's look at this. Z is here. Z is here. So let's look at the. Let's buy some space. I really appreciate it. I don't know who asked these questions about the annulus. First asked these questions. But I can only tell you that annuli are very important. So let's look at F plus. So where's my picture of my annulus? Let's. Here's the integral around the outside boundary. Zeta's in the middle. So the integral of f plus of zeta is, let's look at it. Let's write it down slowly and look at it. On the disk of radius 1, is f of zeta divided by 1 over z minus zeta. And zeta is inside the disk and z is on the outside of the disk, so we factor this out and we write it like this. Right? Right? And then we write it, this integral, as this the sum, and let's just write it, the sum of a n z zeta to the n. So I'm I'm reproving the formula for power series equals and now what is a n? We write it down, right? See if you can do this in your head better than I can. Integral around the boundary of the disk. I think it's completely clear. F of z over z to the n plus 1 dz. Isn't that true? There's an expanded geometric series and that's it, right? We expand this in the geometric series, and when we do that, we get zeta over zeta to the n over z to the n, but we have another z here, so we get z to the n plus 1. This is converging on the disk. On the disk. Well, what about AF minus? Everybody in this room could write down F plus minus F minus. And now we have to figure out where this thing is good. 1 over 2 pi I, integral around the boundary of the inside disk. This one's the radius r. And now, in that case, z is in here, and z is smaller than zeta, because it's on the inside disk. So we divide by zeta. So we divide by zeta. So f of zeta. And I put the minus sign out here already. So f of z divided by zeta. Zeta 1 minus z over zeta. Because I already put the thing out there. Right? And this is equal, same argument, to a power series, an, let's go n equal, okay, for the heck, no, why not? No, why? N equals 0 to infinity. Maybe I put it here, put a hat on this. Zeta to the minus n, right? No, because when I expand this out, I get zeta. The first term is the constant term, but I have a zeta here already, right? So minus n, and then a hat is integral over the inside boundary of f of z. Now the way I let this run probably is z to the n, I think. You will have to check whether it's z to the n or z to the n plus 1. I never know here, but I made a mistake. I don't want to do it out. Right. Okay. So this is equal to sum a n hat over zeta to the n. Yeah. And this thing is here, sum a n hat zeta to the. And now where is that conversion? It's very highly non-trivial if you think about it a little bit. The key here was that you're running around the inside boundary and zeta is outside. It doesn't matter where the heck zeta is, zeta could be out here. Right? So this is f equals f plus minus f minus, where f is holomorphic on the inside disk. And f minus is homomorphic outside the inside disk, homomorphic on the outside disk. So we have an annulus. Right? We have an annulus here, and this annulus is somehow the intersection of an inside disk intersect outside disk. Inside here, inside here, outside here. F is holomorphic, is meromorphic. Any meromorphic function, even with the singularity and so on, is the difference between something holomorphic on the inside and something holomorphic on the outside. Right? Yeah, the inside power series is of course a power series in F is a power series Let's use a variable in Z, and F minus is a power series in 1 over Z. F is a convergent power series, F plus is a convergent power series in Z on the inside. F minus is a convergent power series. That's a global result, but proved somehow locally coming from looking at the singularity. Very, very interesting. Okay. Riemann thought about this. Riemann invented manifolds. He was maybe your professor in calculus on manifolds told you that. Maybe not. Riemann invented manifolds. And Riemann said that manifolds should have charts and coordinates. Charts and coordinates, right? The statement is here, F is the difference of two things. This thing here in the coordinate Z, and this thing here in the coordinate 1 over Z. Change of coordinates goes from Z to 1 over Z. If you look at it that way, it's very, very interesting. You have two disks, one with coordinate Z and one with coordinates, I don't want to call it zeta. The change of variables is zeta is equal to 1 over Z. That's effectively the gluing of these two disks together. And it says, if you take on the intersection of these two disks, on the intersection of these two disks, you have a function. You can write it as a function on the one disk minus the function on the other disk, but you write it in terms of two different coordinates. One coordinate is 1 over the other coordinate. That's exactly how Riemann thought. Okay. And then he even wrote something that I didn't understand because my professor never told me how to understand this, but my professor understood it. And Riemann understood it very well. Nowadays we understand it because we understand the notion of a manifold, which was made precise probably at the first time in the 1930s. So Riemann's notation, I think this is Riemann's notation, I'm almost sure, more or less Riemann's notation. C bar. So what Riemann did was he takes the complex plane and he has the complex plane and he adds the point at infinity because he wants to let z 1 over z be a coordinate. He wants to, right, the point at infinity is the 0 in the coordinate 1 over z. Right? So he just adds this in some formal way. So he didn't worry about it at first, but then he defined manifold, and so he knew this should be a manifold. So he takes the one-point compactification of the plane. And now what is this as a real guy? It's R2 plus the one disjoint union 1 point. Well, everybody here knows, because we know this from the atlas. This is our sphere, right? Everybody in the past was able to understand that there is this mapping. If you go to infinity, let's say the North Pole, I don't know whether I want the North Pole to be infinity. Yes, let's let the North Pole be infinity. Yeah, that confirms that n is big N. And that's the South Pole should be 0. Right? And now, the sphere is not our Earth, but but what we can do here is we can project every point on the plane except that. So we start at the North Pole and we project everything onto the plane. And this is the atlas. So the atlas is this plane with this projection. And the reason you have this big book, it's called the Shell Atlas. I've told you about this in Germany. It's a wonderful book because it contains all the projections. Right? There are projections of anything, but this is a good one. And this is the projection from the north, so you can project it on the complex plane. Right? Or you can project it from the south, and that's another projection. And the coordinate you get on the north projection, south projection are one over the other. There are two coordinates, and you know what this is. You see the sphere. You see the sphere. Well, it's pretty interesting. What is the sphere? The sphere is the annulus on the intersection. So this disk inside. And this disk outside, and the gluing is on the gluing is on across the annulus. The gluing is across the annulus. You see it here in this picture. Oh, there's a sphere, right? Well, I'll do it here. Here is a. Well, let's even make here. Let's make the overlap only the equator. Right? Then you have this disk glued with this disk along the boundary. Now what we're doing over here is we're having an intersection of these two disks. We're having intersection of the two disks. So here's the top disk. Here's the top disk. And maybe this is the top disk. I don't know. This is the top disk. Right? And then this and the intersected with the bottom disk. So I allowed intersection here. Here's the intersection with the bottom disk. Well, the bottom disk goes up to here. And then the intersection is the annulus. And it says that every function holomorphic on the annulus is extendable. It's interesting. Even though it has a singularity at 0 and so on, it's extendable almost in some sense. It's the difference of a function on the inside disk minus the function on the outside disk. Here, the inside disk is here, so F plus is pink, and F minus is I don't know whether I put plus and minus. And F on the annulus here is then F plus minus F minus. Okay. That's one huge motivating factor for understanding what the hell is a manifold. Right? Because you have a coordinate on the inside disk Z, and a coordinate on the outside disk zeta, and Z and zeta differ by 1 over. Okay. That's your first Riemann surface. Okay, so I've given you 2 coordinate charts, and I told you to change the coordinates. Yeah. 2 charts. So Z disk and zeta disk. I just followed Riemann's notation, and zeta equals 1 over Z on the intersection. Now, I have one remark that should make you excited. Forget complex analysis. and think in terms of calculus on manifolds. Take a disk. Yeah, here's a disk. Take another disk, and now you glue right at the boundary, say. Now this gluing is 1 over z. That reverses in some sense orientation, but it has to because, right? It has to because this disk has another orientation, right? As a disk. That's a perfect gluing. You get the 2-sphere. Okay. Now, take the 3-sphere. Take the equator on the 3-sphere. That's a 2-sphere. You see, this intersection here, this boundary here is an S1. S2 is made by gluing 2 disks along an S1. S3 is made by gluing 2 disks of dimension 3 along S2. All right? S4 is made by gluing 2 disks of dimension 4 along an S3. Right? Etc. Etc. What happens as n goes to infinity? Is there something interesting? There is absolutely nothing interesting in dimension 2. Everything is the 2-sphere. Then dimension 3. You start getting pessimistic, nothing happens. But then you ask the right question, which everybody here could ask. What is a gluing? Yes? What is a gluing? A gluing, up to orientation, is just a diffeomorphism of the sphere. Right? You're not gluing with the identity, you're gluing with some diffeomorphism. Right? Gluing is a map. It's a smooth map, so it's a diffeomorphism of the sphere. You glue this point to that point by a diffeomorphism. It's just very simple. You have a disk of dimension n. You have the sphere of dimension n minus 1. You have another disk of dimension n. You get the orientations right. You have the sphere of dimension n minus 1, and you glue here from here to here by a diffeomorphism. Yeah. And you ask, particularly you're a physicist because you know spheres are important. You don't believe me, spheres are certainly important in physics. What the heck do you get here? And so you are led to try to understand the diffeomorphism group, the diffeomorphism group that glues. Right? Isn't that what you're supposed to understand? Okay. Guess what? You get non-trivial examples, starting in something like 5. Okay. This is an extremely beautiful subject. What are the different examples that you get by gluing? Yeah? Very interesting. In dimension 2, you only get the 2 spheres. But keep in mind, in higher dimensions, you get non-trivial things that are not the classical sphere. Okay, so see you tomorrow. We do have the extra lecture tomorrow.